None can escape the allure of mystery, especially when it involves a cat that is both alive and dead. In 1935, physicist Erwin Schrödinger proposed an experiment that would baffle minds for decades. A cat, a sealed box, and a vial of poison. Is the cat alive or dead? According to quantum mechanics, it's both until we look inside. Can something be in multiple states at once? What does it mean for our perception of the universe? You are watching documentary, a gateway to questioning everything we think we know about existence. So what did Schrödinger's cat experiment prove? Schrödinger's cat was not a real experiment, and therefore it did not scientifically prove anything. In fact, Schrödinger's cat isn't even part of any scientific theory. It was simply a teaching tool that Schrödinger used to illustrate how some people were misinterpreting quantum theory. Schrödinger constructed his imaginary experiment with the cat to demonstrate that simple misinterpretations of quantum theory can lead to absurd results, which do not match the real world. Unfortunately, many popularizers of science in our day have embraced the absurdity of Schrödinger's cat and claim that this is how the world really works. In quantum theory, quantum particles can exist in a superposition of states at the same time and collapse down to a single state upon interaction with other particles. Some scientists at the time that quantum theory was being developed in the 1930s drifted from science into the realm of philosophy. They stated that quantum particles only collapse to a single state when viewed by a conscious observer. Schrödinger found this concept absurd and devised his thought experiment to make plain the absurd yet logical outcome of such claims. In Schrödinger's imaginary experiment, you place a cat in a box with a tiny bit of radioactive substance. When the radioactive substance decays, it triggers a Geiger counter which causes a poison or explosion to be released that kills the cat. Now, the decay of the radioactive substance is governed by the laws of quantum mechanics. This means that the atom starts in a combined state of going to decay and not going to decay. If we apply the observer-driven idea to this case, there is no conscious observer present. Everything is in a sealed box, so the whole system stays as a combination of the two possibilities. The cat ends up both dead and alive at the same time. Because the existence of a cat that is both dead and alive at the same time is absurd and does not happen in the real world, this thought experiment shows that wave function collapses are not just driven by conscious observers. Even Einstein saw the same problem with the observer-driven idea and congratulated Schrödinger for his clever illustration, saying, "This interpretation is, however, refuted most elegantly by your system of radioactive atom plus Geiger counter plus amplifier plus charge of gunpowder plus cat in a box, in which the psi function of the system contains the cat both alive and blown to bits. Is the state of the cat to be created only when a physicist investigates the situation at some definite time? Since that time, there has been ample evidence that wave function collapse is not driven by conscious observers alone. In fact, every interaction a quantum particle makes can collapse its state. Careful analysis reveals that the Schrödinger cat experiment would play out in the real world as follows. As soon as the radioactive atom interacts with the Geiger counter, it collapses from its non-decayed/decayed state into one definite state. The Geiger counter gets definitely triggered and the cat gets definitely killed, or the Geiger counter gets definitely not triggered and the cat is definitely alive. But both don't happen. Roger Penrose, a Nobel Prize winner and one of the most brilliant physicists of the last 60 years, wrote about Schrödinger's cat in his book The Road to Reality as follows. So the cat is both dead and alive at the same time. Of course, such a situation is an absurdity for the behavior of a cat-sized object in the actual physical world as we experience it. There is a 50% chance that the cat will be definitely killed, and a 50% chance that it will definitely remain alive. This is the physically correct answer, where physically refers to the behavior of the world that we actually experience. Penrose goes on to explain that any physical theory or philosophical interpretation of quantum physics that leads to the cat being both dead and alive at the same time must be a faulty theory or interpretation, because that is not what happens in the real world. Despite the fact that Schrödinger's cat is not a real experiment, does not prove anything, does not match physical reality, and was intentionally designed to be absurd, this line of thinking does indeed lead to a meaningful question. Why does the cat in this setup not end up in a state of dead and alive at the same time in the real world? In other words, why does a measurement collapse a quantum object from a superposition of states to a single definite state? This question has not yet been fully answered by quantum physics. This is known as the measurement problem of quantum physics. Note that the measurement of a quantum object in a superposition of states collapsing down the object to a definite single state is very well predicted by the mathematics of quantum physics. Therefore, the measurement problem is more a problem of philosophical interpretation and incomplete scientific explanation than a problem of the theory being incorrect. In summary, quantum state collapse is not driven just by conscious observers. Unfortunately, many popular science writers in our day continue to propagate the misconception that a quantum state, and therefore reality itself, is determined by conscious observers. They use this erroneous claim as a springboard into unsubstantial and non-scientific discussions about the nature of reality, consciousness, and even Eastern mysticism. Before we cock and lewd, let's take a moment to understand the man behind the famous thought experiment, Erwin Schrödinger. Born in Vienna, Austria in 1887, Schrödinger was a brilliant physicist whose work laid the foundation for much of modern quantum mechanics. Known as the father of quantum physics, Schrödinger's contributions extend far beyond his infamous cat. He was a versatile thinker, deeply influenced by philosophy, literature, and the arts. Schrödinger's approach to science was holistic. He believed in the interconnectedness of all knowledge, which is evident in his interdisciplinary works. His most notable achievement, the Schrödinger equation, revolutionized our understanding of quantum systems. This mathematical formulation describes how the quantum state of a physical system changes over time, providing profound insights into the behavior of particles at the smallest scales. Yet Schrödinger's intellectual curiosity didn't stop there. He published works on color theory, thermodynamics, and the philosophy of science. His book, What is Life?, explored the relationship between biology and physics, inspiring future generations of scientists, including molecular biologists who would later discover the structure of DNA. Despite his monumental contributions, Schrödinger remained a humble and introspective figure, often contemplating the philosophical implications of his scientific discoveries. In conclusion, Schrödinger's cat experiment challenges our understanding of quantum mechanics and reality. It illustrates the paradoxes and complexities of quantum theory, leaving us with more questions than answers. The experiment remains a cornerstone in the study of quantum physics, provoking thought and debate among scientists and philosophers alike. But what does this all mean for us? Schrödinger's cat isn't just a thought experiment confined to the realms of academia. Its implications ripple through various fields, from the technology we use daily to the philosophical questions we ponder about existence and observation. Consider the devices we rely on: smartphones, computers, and medical imaging equipment. These innovations owe their existence to the principles of quantum mechanics, principles that Schrödinger's equation helped to define and understand. Each time we use these technologies, we are indirectly engaging with the quantum world. Schrödinger's cat forces us to confront the nature of reality itself. Are we living in a universe where multiple possibilities exist simultaneously? How does our act of observation influence the world around us? These are not just scientific questions, but philosophical ones that challenge our perception of existence.